Welcome to Chapter 2. In Chapter 1, we described single random variables. Now we ask what happens when we average many of them, which is what every experiment does when it reports a mean. Two theorems answer that. The law of large numbers says the sample mean settles onto the true expectation as the sample grows, and it comes in a weak form and a strong form. The central limit theorem goes further and tells us the shape of the remaining error. It is normal, no matter what the original distribution looked like. We will state both, verify them by simulation, and apply them to material strength data. The weak law concerns independent, identically distributed variables with a finite mean mu and a finite variance sigma squared. It states that for any tolerance epsilon, however small, the probability that the sample mean differs from mu by more than epsilon tends to zero as the sample size grows. This is called convergence in probability. The proof is short. Chebyshev's inequality bounds that probability by the variance of the sample mean divided by epsilon squared, which is sigma squared over n epsilon squared, and that clearly goes to zero. Note the bound is often loose, but the conclusion is exact and it does not depend on the shape of the distribution. The strong law of large numbers makes a stronger statement using a weaker assumption. It requires only that the expectation of the absolute value is finite, and it concludes that the probability that the sample mean converges to mu equals 1. That is almost sure convergence. Compare the two carefully. The weak law says that at each fixed large n, it is unlikely you are far from mu, but it permits occasional excursions forever. The strong law says that essentially every individual path eventually settles arbitrarily close to mu and stays there. Almost sure convergence is the stronger condition, and it implies convergence in probability, not the other way around. Knowing that the average converges is useful, but experimenters need to know how fast. Simulate many independent paths and summarize them with a confidence band, and you see the band narrowing smoothly around the true mean. Plot the variance of the sample mean against n on log-log axes, and it follows sigma squared over n take the square root, and you get the standard error. Sigma over the square root of n, that square root, is the practical lesson of this chapter. To have your uncertainty you need 4 times as much data, and to reduce it tenfold you need 100 times as much. Precision is expensive. The central limit theorem is the reason the normal distribution appears everywhere. Take independent, identically distributed variables with mean mu and finite variance sigma squared. Standardize the sample mean by subtracting mu and dividing by sigma over the square root of n. That standardized quantity converges in distribution to the standard normal, meaning its cumulative distribution function approaches phi, the standard normal cumulative distribution. The remarkable part is what the theorem does not require. The original distribution can be flat, two-valued, skewed, or bimodal. As long as the variance is finite, the standardized sample mean becomes normal. Simulation makes the theorem concrete. Here we take 4 very different source distributions: a flat uniform, a two-valued Bernoulli with success probability 0.3, a skewed exponential, and a U-shaped beta with both parameters at 1/2. For each, we draw samples of size 1, 5, 30, and 100, compute 10,000 sample means, standardize them, and histogram the result against the standard normal curve. At n equal 1, each histogram simply reproduces its own source distribution. By n equal 30, the bell shape is clearly emerging, and by 100 all 4 rows look essentially identical. Different origins, one common limit. Let's stress test the theorem with a strongly skewed log-normal distribution, which has a long right tail. Repeating the experiment, at very small n the standardized sample mean is visibly lopsided and clearly not normal. As n increases through 5, 10, 30, and 100, the histogram straightens up and settles onto the standard normal curve. We can test this formally rather than by eye with the Kolmogorov-Smirnov test, comparing the standardized sample means against the normal distribution. The lesson is practical. Heavy skew does not break the central limit theorem. It just means you need a larger sample before the normal approximation is trustworthy. When the population itself is normal, we know the sampling distributions exactly. The sample mean follows a normal distribution centered at mu with variance sigma squared over n, so its center is unchanged and its spread shrinks with the sample size. The sample variance, computed with the n-1 divisor to make it unbiased, is related to the chi-square distribution. n-1 times s squared divided by sigma squared follows chi-square with n-1 degrees of freedom. And when we replace the unknown sigma with the sample standard deviation s, the resulting t statistic follows students' t distribution with n-1 degrees of freedom, which has heavier tails. Here is why this matters in materials science. Testing specimens is expensive, so we estimate population properties from a handful of them. The strength of brittle materials typically follows a Weibull distribution, which is skewed and definitely not normal. Yet the central limit theorem tells us the average measured strength across specimens is approximately normal, and that is exactly the quantity we report. That justifies using t-tests and building confidence intervals even though the underlying strength distribution is not normal. As the number of specimens grows, the standard error shrinks like sigma over the square root of n, and the confidence interval tightens accordingly. To summarize, the weak law says the sample mean converges in probability to the true mean, and Chebyshev's inequality gives an explicit bound. The strong law upgrades this to almost sure convergence of individual paths. The precision of an average improves like sigma over the square root of n, so cutting the error in half costs 4 times the data. The central limit theorem says the standardized sample mean becomes normal whatever the source distribution, and the sample mean, sample variance, and t statistic all have known sampling distributions. In Chapter 3, we let randomness evolve over time, with Markov chains and Poisson processes.